In this video, I'm going to talk about chapter 9 of my book with Roberto. It is about Gauss-Manin connection from topological and algebraic point of view. So first, what is Gauss-Manin connection from a topological point of view? Let's assume that we have a family of smooth projective varieties. So its fibers be denoted by xt. So here is the parameter space capital T, and our point, let's say here T, then we will have the M cohomology of xt, and the rank cohomology with complex coefficients. If we ignore torsions of singular cohomology, inside this cohomology, we have also singular homology. So we have this cohomology bundle, and this cohomology bundle have this very special flats whose image will be here. This gives us these are going to be actually the flat section of Gauss-Manin connection. So in a small neighborhood U of T, we can find the sections S1, SB such that any order holomorphic section U can be written as a combination of SI with FI being holomorphic functions in U. And then we define this connection on the cohomology bundle, which send this sum of FI SI to a DFI tensor SI. So by definition, SI nabla SI is zero, and so this means that SI is a flat section. Before defining the algebraic Gauss-Manin connection, we have to define what is cohomology bundle in the algebraic geometric framework. For this, we need to define the sheaf of relative differential forms. So these guys for us will be zero. And it turns out that we have a complex of the relative differential forms. And so when we have the complex, then we can define the relative algebraic de Rham cohomology in a similar way as the non-relative case. Remember that for our computational purpose, we take a covering with affine open sets. This will be a good covering for us because we are using differential forms. And then we form this double complex. And then going up is delta, going to the left is t, and then we define we define this capital D operator from Lk to Lk plus 1. Remember that this was L0, this was Ly, this was L3, and so on. And the algebraic de Rham cohomologies is just the total, the cohomology of this usual complex L dot D. Now, one very important fact that everything is done over an arbitrary field k of character 0, and when we have started from a smooth projective variety over k, then the relative de Rham cohomology is a free sheaf of finite rank of OT modules. And in a more geometric language, they are sections of a vector bundle, which we call it a cohomology bundle. In the book, we have presented two proofs for this fact, the topological and algebraic proof, and I will skip the proofs here. Let us now try to define the algebraic Gauss-Manin connection. So we have defined the cohomology bundle as a relative theorem cohomology. The sheaf of differential one formed in T is algebraic because T itself is algebraic. So what is this knot that we already saw in the topological context? For this one, we have, for simplicity, we will take T aspect of some ring and we will distinguish these two differential. So dr will be the differential of the relative theorem cohomology, and why we put r? Because for this dr, the elements of R are constant. Whereas when we take differential forms on X itself, the constant of the differential form will be elements of the field. So these elements will be no more constant. Remember that we defined our relative theorem cohomology using this double complex. From another side, we have this double complex of differential forms on X, and we have a canonical projection from this one to this one here. So we take element omega 0 plus omega 1 in H M theorem X over T, and we take a representative of this one in this double complex, and we denote it by omega 0 check plus blah 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 omega n check. So we have a differential of the relative case of omega equal to 0. When we apply the now differential non-relative one, dx of omega hat will be an element like this, and this must be 0 in the relative version of differential form. So this means that omega hat I will have this beta I alpha I part, and then here we'll have alpha I in omega 1. And, and we simply map this element to element here, replacing the wedge with the tensor sign. And now we are claiming that this is almost the image of the Gauss-Manin connection nabla of omega. For this, we have to check that the image of the we have to check that this happens, and remember that we these new differential form they have coefficients in omega 1t, and in this way we can transport this guy into an element in omega 1t tensor with h m theorem x over t. In order to prove this identity, we use the fact that omega t or omega 1t, which are differentials of the ring R, are generated by exact form. And from this exactness, we will just use the closeness. And then we start from this identity, and then the first dx, we just substitute the definition that we had here, and assuming that alpha us are closed, then we will have this this identity. And this will imply that identity in the omega 1 t part tensor with d, the relative differential operator of the element that we have get is zero. And finally, we define the algebraic Gauss-Manin connection with this as this one appearing this minus 1m there. The fundamental property of the Gauss-Manin connection is this theorem which relates it to integrals, and that is why the name of Gauss appears. So these integrals will be holomorphic functions in T, so we can take its differential, and its differential will be the integral of delta T of the value of the naught over omega, remembering that the integration is not taken in the omega 1 t part, these are just constant, and it is taken in the cohomology bundle part of the, the element. So the same theorem with different language used is say that the Gauss-Manin connection that we introduced in the beginning of our video is the same as the algebraic Gauss-Manin connection that we discussed. And one important part of the proof is this proposition 31 in my book, which is basically the same equality that we wrote in the framework of affine varieties. So in affine variety, we don't need really to use hypercohomology because variety Hodge theorem elements of the rank homology are already represented by algebraic differential function. So let's close this video with some fundamental properties of the Gauss-Manin connection. One of them is the integrability. So actually, any connection will induce this kind of maps, which are defined by this, and the composition of two consecutive such maps is zero. This is called the integrability condition. The next important property is the relation of Gauss-Manin connection with Hodge filtration. So in a similar way, we'll have Hodge filtration of the cohomology bundle, and it turns out that the Gauss-Manin connection of Fk goes to Fk minus 1. So it's a kind of pushing forward. Remember that Fk was inside Fk minus 1, and blah blah blah, and then there is everything is inside f0. The proof of this fact is just the definition of the Gauss-Manin connection. Remember that we take the representative, we make its dx, we go forward, and when you look at this element, we will already realize that if we were in omega k, then the image here, if you have eta k check, and above it everything is zero, is here above this one everything is zero, and so from fk we have jumped to fk minus 1. Few other properties of the Gauss-Manin connection is scattered in this proposition. So the polarization that we called it theta is a flat section. So this is a kind of natural. It's compatible with all our knowledge of topological Gauss-Manin connection. because remember that polarization was the cohomology class of the hyperplane section, and this is in singular cohomology with integer coefficient. And since we have defined the Gauss-Manin connection using the usual differential, it is natural to expect also this second property, which is derived from a similar property for the differential d, and also the fact that the nabla sends the primitive cohomology to itself, and so it will respect the Lefschetz decomposition. A more elementary version of Gauss-Manin connection is presented in chapter 12 of my book. It contains a historical account of the Gauss-Manin connection, which is basically quite like this derivation of some integral, which depends on some parameters. It goes inside, and this was this. Remember that this was written in 10 minutes ago as something like this: nabla omega delta. For example, in this exercise, we consider just a family of elliptic curve y px, and you see that px depends on three parameters. So we take the differential of the integrals over some cycle with respect to these three parameters, and it turns out that this dx over y, x dx over y, are bases are two sections of the cohomology bundle here, such that at each point they form a basis. So we can write this differential here. I have what this, let's say in the usual language that I explained it. There's a tensor here, and so here we have differential one form in omega one t, and then the integrals here. And if I want to write down this without the integral range, so without this integral range, we could just remove the integral sign. Here, put px just y, and here put tensor sign, remove integral, and that is the Gauss-Manin connection in the sense of Gauss. I hope you enjoyed this video.